Okay, let's talk about this. Again, it didn't take much time because they're just 3 short questions. The first question is asking us about the acceleration. And I hope no one missed this question. This is where we've been. This is not a pre-test, this is a post-test. We know that because that crate is still moving down, its velocity vector is down. And because it's slowing down, the acceleration vector is up. That should be trivial now, okay? Now, the bigger question, the pre-test question, is number 2. And that is comparing 2 forces that are acting on this crate. The first one, the gravitational force, the weight. You know, if you took this crate in and you said, I want to ship this to my brother, and they put it on the scale and they say, oh, that's 50 pounds. That's going to really cost you a lot. The weight force would be 50 pounds. Simple as that, okay? And the question is, the upward force by the snow, we're going to talk more about what flavor that force is later, but for now it's just the upward force by the snow. And the question is that going to be greater than 50 pounds, equal to 50 pounds, or less than 50 pounds, where 50 pounds is the weight of the crate? Now, you just answered that, so why don't we use our clicker to tell me how you answered. Okay. Last call. Get your vote in. Oh, it looks like there's an opportunity for learning. Now, folks, we're not going to collect that pretest, but I would like you to write at the top of it, this may be wrong, okay? So that when you're studying for the next exam, you don't think you got truth there on that page, because clearly some of you do not. Let's talk about it. We have just been talking about kinematics or motion, and now we're moving to dynamics or the study of forces. And the relationship between them is often described as forces cause motion. And if that's what you learned today, you will fail the next exam. Do I have your attention? Okay? That's just not so. The truth is ever so subtly different. Here it is. Watch. Here it comes. Here it comes. Pow! You want to see that again? Pow! Forces don't cause the motion. They cause a change in the motion. And that's the biggest source of confusion for beginning students in physics. Okay, so we're going to address that in this week's tutorial and next week's tutorial. Now, the tutorial, you haven't received a link for that yet. And that's because I really didn't want you to watch that tutorial video until after today's lecture. Okay, now the tutorial homework, which is normally due Friday at midnight, is not due until Saturday midnight, so that we can ruin your general conference weekend. Sorry. Okay. Now, we're going to have to do some name calling. I need my my helpers again. Okay. Thank you, Luke. Who's over here? Got a laugh last time. We do in front. There you go. Sure.
And you get one day to do it.
Okay, I'm gonna, share with you a very important truth.
Oh.
President Uchtdorf, when he was in the first presidency, told a story about, well, airplanes, you might expect, where the pilot was off by just a fraction of a degree, and they ended up miles away from where they were supposed to be in the down in the Antarctic. Anyway, the point of his talk was that you can always repent, you can always fix things along the way. And that works in life, not so much in physics, okay? In physics, every dynamics problem, force problem, starts the same way. We draw what's called a free body diagram, where we identify all the forces that are acting on the object we're studying, all of the forces. And here's the thing, if you start with the wrong free body diagram, you have zero chance, absolutely no chance of getting any of the rest of the problem right. And so the key is getting that free body diagram accurately drawn. And I'd like right now to show you a recipe. If you follow the recipe, you'll never, ever get your free body diagram wrong. Now, I didn't come up with this. I learned it when I was old from Lillian McDermott, and it just opened my mind. I just, oh, why didn't I know this earlier? And so I want you to learn it at your tender young age so that you don't have to go through life without it. Now, first of all, we have to understand the different flavors of force. And the way we try to divide things up is we divide all macroscopic forces up into two categories, either contact forces or non-contact forces. Now, let me give you an example. I go out and I sit on the quad, it's not raining, it's sunny day, and I eat my lunch. The earth is pulling down on me with a gravitational force. I'm touching the earth and me are in contact. Is that gravitational force a contact force or a non-contact force? It's a non-contact force, because we just talked about it last week. If I jump off a cliff into a pond below, I'm not touching the earth, but the earth is still pulling down on me, okay? The issue is not whether you're in contact, but whether contact is required, if it has to have contact. If I come and punch Luke from over here, he's not worried, okay? There's no contact, there's no force going on there. Now, the very first non-contact force, that we put on every free body diagram is the gravitational force. Now, we're going to learn that everything with mass attracts everything else with mass, but the attraction of my head to this book is so teeny tiny, we're going to ignore it. But when one of the objects is huge, like the Earth, that's a considerable force. We call those weight forces. We'll use a W to indicate that. And folks, I'm here to tell you, you can only change that through diet and exercise, okay? Now, the electromagnetic force, it turns out we can divide that up into two forces, the electric force and the magnetic force. The electric force is going to be one of the main topics of Physics 106. We're going to study that a long time, okay? But we're not going to speak of it in 105. But we all have refrigerator magnets holding up our artwork on the refrigerator, okay? So we're going to talk about magnetic forces at that level, just refrigerator magnets attracted to refrigerators, a non-contact force, okay? So this is the recipe. When you are drawing your free body diagram, looking for all the forces acting on an object, you first of all put the weight force every time straight down towards the bottom of your page, center of the earth. Second, you ask, are there any magnets in this problem? Usually no, but every now and again, yes. On the exam, definitely yes, okay? And once you take care of those two non-contact forces, all the other forces are due to something that actually touches your object, okay? Now you'll notice there's another square up there in the non-contact category, and that's the nuclear forces or nuclear forces, depending on who your president was, okay? Now, those are the strong force, the weak force. We're never going to speak of those again. They don't apply to classical physics. They just don't crop up in what we're doing, okay? So for us, it's just the gravitational and the magnetic. Now, how do I deal with the contact forces? Well, I make a list of all the things that physically touch the object that I'm drawing the free body diagram for. And for each one of those things, I asked, does it push or does it pull? Well, strings pull, threads pull, ropes pull, and chains pull. If it's not one of those, it pushes. Well, let's talk about the pull. That's the tension force, and we use a capital T to label a tension force. Now, tutorial 5 on tension, I call the mother of all tutorials. If you're going to cry during a tutorial, it'll be due to number 5, okay? And we'll get through it. We'll get through it. But we're just going to hold off for now. We'll just anticipate that coming, okay? Now, let's talk about pushes. If it's not a string and not a rope, not a chain, not a thread, it's a push. Now, I want everyone to clear a space in front of you on the little table that you've got. And I want you to push down with your hand at some arbitrary angle, like 53 degrees, you know, something like that. Keep pushing, okay? Now, what you should be feeling right now are two sensations. You should be feeling a pressure on your palm, and you should also, I didn't say you could quit, keep going. You should be feeling a pressure on your palm, and you should also feel the skin being pulled back on your bones, okay? Okay, now you can stop. But what I want you to do now is to gently lay your hand down on that table, and with your other hand, push down perpendicular to the table, perpendicular, until you feel the same pressure that you felt before. What's missing is the skin, don't stop, keep going. What's missing is the skin pulled back on the bones. So while you're pushing down, ease your hand forward, your bottom hand forward, until you get that pull of the skin on your bones that you felt before. Now, what you can stop now, okay? Yeah, you don't do that, you don't learn. What we did is we divided up an arbitrary push into two separate pushes that are very, very different from each other. The first was that perpendicular push, and we call that the normal force. And that's not to say that all the other forces are abnormal. Normal is what mathematicians say when they mean to say perpendicular, okay? I have been to their parties, people. They do not know what normal means. They are not normal, okay? So this normal force, we will label with a capital N, and it's always perpendicular to the interface between the pusher and the pushee, okay? Now, it turns out that normal force is the most common force on our free body diagrams. Whenever one thing pushes on another, there will always be a normal force. There may also be a second force, and this is the force that causes the skin to pull back on the bones. What's happening is the nooks and crannies of the table are grabbing the nooks and crannies of my hand and pulling on them. And we call that the friction force. And for historical reasons, we use a small letter F to indicate that. And that's one of the more tricky forces. We're going to deal with it in a week, next Tuesday. It turns out that can cause confusion. But for now, it's just that horizontal or parallel to the surface grabbing of nooks and crannies from one surface to the other. Okay. Now, yes.
Is it kind of like in a different way, like the same thing with the vector, like the velocity vector, like there's a vertical vector.
Well, we are going to divide pushes up into components, but in this case, it's not going to be a Y direction and an X direction. It's going to be a perpendicular and a parallel. So for example, this would be a normal force, and this would be a normal force, and pulling up would be a normal force, as long as I'm pushing perpendicular to the surface. So it's not always the X direction or the Y direction that's the normal force. Did that answer your question? Okay. Now, when we draw our free body diagrams, we will label our forces by one of these 5 labels. It's either a W, a weight force, it's either a M, magnetic, little f, friction, big N, normal, or a big T, tension. We won't label any of our forces with just a big old capital F. And that's not because Greg's picky. I'm not. I'm a live and let live sort of guy. But Lillian McDermott taught me this approach to make sure that you never, ever, ever get confused about Newton's third law, which is what we're going to talk about on Thursday and is the topic of this week's tutorial. Now, on Thursday, I'm going to induct you into a club. It's the I Understand Newton's Third Law Club. And it's not a big club. It's very exclusive. I'll tell you how exclusive. For 15 years, I was serving on a 3-person committee where I would go once a year to Chicago to the American Dental Association to write the entrance exam, not for the dentists. They don't have to know physics. I don't understand that, but they don't. Oh, there's no physics on the DAP. However, the optometrists need physics on their exam, and they didn't have a test making facility, so they subcontracted out to the dentists. So every year I would write this entrance exam, the physics portion, for the optometrists. And every year I tried to put a third law question on the exam. But they had a policy that they would pre-test all of the questions that I wrote. And if 40% of the students that were pre-tested couldn't get it right, they would say well, that problem's way too hard. And so for 15 years, I tried to put a basic third law question on this exam. They never got more than 40% of the students to get it right. Finally, I gave them a question that just had the right answer, and then the distractors, I put red, green, and purple, and they just said, you can't do that. Well, that's the only way they're going to get it right. So anyway, we're going to understand Newton's third law. Okay, let's talk about those free body diagrams. Let's draw one for the Greg. Okay, so the first force I put on there is the gravitational force. That's the gravitational force, the weight force by the Earth on the Greg. All of our macroscopic forces are a dance between something that's doing the pushing and something that's experiencing the pushing or pulling. Okay, it's always something exerting the force and something experiencing the force. And so we'll label all of our forces by on, and this will help us with Newton's third law. And then I asked, are there any magnets in the problem? No, I don't have any magnets anywhere near me. And then I asked, what's touching the Greg? Well, the floor. Does it push or does it pull? Not a string, not a thread, not a rope, not a chain. So it pushes. Whenever one thing pushes on another, there will always be a normal force. In this case, by the floor on the Greg. And it's perpendicular to the floor. And since the floor is beneath me, that's a push up. Okay? Now, whenever one thing pushes on another, there will always be a normal force. There may also be a friction force. Maybe, maybe not. Well, how do I know, Greg? Well, imagine greasing down that surface and ask if that changes anything. If I'm just standing here and we've greased down that floor, does it change anything? No, I can still stand here just fine. But if I try to walk, I fall on my face. So if I'm just standing here, that's the right free body diagram. When I start to walk, there has to be a friction force there, or else I'm going to fall down. Okay, so that's how you follow the recipe, and then you're sure you're not missing any forces. See if your neighbor's on the bus. See if they understand these free body diagrams. Okay. Many years ago, a few years before you were born, Aristotle tried to reason about motion, and he made observations, did experiments, and found that when he got things moving, they just always stopped. Okay, and so he reasoned that the natural motion was stopped. That's what things wanted, was stopped. He had different rules for the heavenly bodies because they didn't stop, but that was complicated. Now, that brings up an important question, and that is, what is the velocity of this room? Well, relative to what? Well, suppose we had an alien hovering in a spacecraft above the North Pole, okay? And we know that the Earth goes around once a day, and we know that once around is 2 pi r, where r is the radius of the circle that you're going around. And so that means that if we plug into that formula with delta t being 24 hours, we get a speed of about 400 meters per second, or 900 miles an hour. Okay? Now, this room is heading that way at 900 miles an hour. And the question is, if I jump up, why doesn't that wall smack me in the head going 900 miles an hour? And after that exam, some of you are saying, yeah, why not? That's the demo we want to see. Jump up again, Greg. Let's see if it works. Okay. And the answer that that we come up with, thanks to Galileo, is that we're also moving at 900 miles per hour, 400 meters per second. And we want to keep going at 400 meters per second. Okay. Now, Galileo, he was known for his thought experiments. Okay, he wasn't so big on actually doing experiments. He was great on sitting in his chair and thinking about experiments. And what he said was, well, what if we take Aristotle's book and we polish the bottom of it? And then we polish the table. Well, when he pushes that book, it's going to go further. And if I make that book more smooth and the table more smooth, it's going to keep going further and further. And then he made the big leap and he said, what if I could get that book perfectly smooth? And what if I could get the table perfectly smooth? And he argued that that book would just keep on sliding forever if the table went forever. Okay. Now, it turns out that Galileo couldn't really test that because he did not have a Reims. I went to Reims this morning and I bought some dry ice, and I'm going to do something with that dry ice real quick. Okay, that's not right. That's not right. Oh, what have I done wrong? There we go. Oh, Greg. Okay. Now, does anyone know why we call this dry ice and not wet ice? Why is it dry ice? No. Nobody? Really? Yes, sir.
Never goes liquid state, it goes straight from solid to gas.
Did he say that it sublimes from a solid to a gas? Yeah, if you put this on your desk and let it melt, it doesn't make a puddle. It goes straight from the solid to the gas. Now, does anyone have a quarter? I might have a quarter. I've got a quarter. Okay, we're good. Two questions. Why does it scream and why does it stop? Talk to your neighbor. Why does it scream and why does it stop?
That's why it's screen. Actually, I like that.
Okay. Why is it screaming, folks? Raise your hand. Where are you? Was that a hand up?
Squeezing around.
What did she say? Luke?
No idea. There are forces coming up around the quarter.
Okay. So because this is warm, it's turning some of the dry ice into gas, and that gas is trying to escape. Escaping gas has been a social problem for a long time, people. Okay, and as it escapes from under the quarter, it causes the quarter to vibrate, and that's what makes it scream. And why does it stop? Yeah.
Temperature equilibrates.
Yeah, the quarter gets just as cold as the dry ice and it stops making gas. Okay, excellent, good. Now, what I can do with this, this table is warm compared to the dry ice. And so it's going to cause the dry ice to sublime. And with that, I can create a layer of gas that will cause this block to float on a layer of gas. Now I have to, first of all, make it smooth on the bottom. It grumbles a little bit. Stop complaining. There we go. Now. No, okay. It's still not smooth on the bottom. We'll get it smooth. Okay. Once I get it smooth. Now, if we push that book across the table, we hear scraping going on. Okay. Listen to hear if you can hear scraping. Now, if we had a table that was 3 miles long, we could get this going and it would just keep going at constant velocity for 3 miles, okay? So if we were a rich school like Harvard, we'd have this table that's 3 miles long and we could do that demo. But who am I kidding? We're richer than Harvard. We got the church behind us. We could buy Harvard 3 times over. Okay, but we don't have any place to store a 3-mile table. So the natural motion is not stopped. It's keep on going. It's keep on going. Now, we're going to do more with that dry ice in just a moment. But for now, let me just acknowledge that Galileo did not use dry ice. He didn't have dry ice. What he did is sit in his easy chair and use some reasoning. And he used what we learned in our first tutorial. He said, if I've got a ball on a ramp, the acceleration is down the ramp. And if the ramp is steep, I get a big acceleration. If it's not so steep, I get a smaller acceleration. And the more shallow I make that ramp, the tinier that acceleration gets. And then he jumped all the way to the other side and said, well, what if I've got a ramp going this way? Well, again, it just makes sense. The acceleration would be down the ramp. And then he took these 2 ramps on the bottom and he made them shallower and shallower and shallower and shallower. And these acceleration vectors got shorter and shorter and shorter. And where they met in the middle, the only answer that was left was acceleration 0. Okay, and so he argued that an object at rest stays at rest, and an object in motion stays in motion at constant speed in a straight line unless acted upon by a net force. Okay, things want to keep on going. They want to keep on going. Okay. Now, I do not believe that it's an accident that the very year that Galileo passed away, this scary man was born. Okay, Newton. He gave us the calculus. Let's just appreciate that for a moment of silence for that. He just brought up the calculus. Thank you, Newton. Thanks for what? Okay. Anyway, he brought us a whole lot of things, gravitation, he brought us a whole bunch of optics, a huge number of scientific discoveries. But he said in his notes, I stand on the shoulders of giants. And I believe the giant that he most meant in that statement was Galileo. Okay, he was born on the same year that Galileo passed away. Now, Newton's first law, and there's 3 of them, is that if there are no net forces on an object, it will have no acceleration. And we understand no acceleration to mean constant velocity. Okay, notice I didn't say constant speed, I said constant velocity. The direction matters. Now, the way we say Newton's first law is this way. An object at rest stays at rest, and an object in motion stays in motion at constant speed. Wait a minute. That sounds like Galileo's law. That sounds like it's plagiarized. And it is Galileo's law. And Newton acknowledged that it was Galileo's law. But we call it Newton's first law because it sets the stage for the second law. It tells us when we can apply the second law in an inertial reference frame. An inertial reference frame is one in which Newton's first law applies. Okay? Now, what do you mean by that, Greg? Well, I mean that if you're sitting in an airplane and you put your little tray down, if the plane's just sitting on the runway and if the tray is level, you can put a marble on that tray and it'll stay put. Newton's first law, okay? If that plane is traveling at 600 miles an hour, but it's a constant 600 miles an hour in a straight line, you can pull down your tray, you can put that marble on it, and it will stay there. Newton's first law. But if you try that experiment while the plane is taking off or landing, first of all, they're going to yell at you. But second of all, the marble's not going to stay there in the middle of your tray. That's not an inertial reference frame. You can't be using Newton's second law in that frame. Okay? Now, let's talk about Newton's second law. It deals with the effective forces on an object. And we're going to use this chart on the back of your page to make an important connection. We're going to do 4 quick experiments. And in these experiments, I'm going to create a motion. And then we're going to write down the direction of the velocity vector, the direction of the acceleration vector, and the direction of the push or pull, not to create the motion, but to maintain the motion. Okay? Now, the first one is just, I have the block at rest. Okay, if the table's level, it just stays there at rest. And that means it has 0 velocity, 0 acceleration. And what do I have to do to keep it there? Nothing. Okay? Now, the next one we've already seen before, and that's just uniform motion to the right. Okay, till it bounces. The velocity is to the right. There's no acceleration. It wasn't speeding up or slowing down or turning. And I didn't have to do anything to keep that going. Now the third one, it moves to the right and speeds up. So if I want it to speed up while it's moving to your right, I'm gonna have to push in the direction that it's going. And if this table were 3 miles long, I'd have to keep on pushing to keep it speeding up, which means I would have to run faster and faster and faster until basically I couldn't keep up as a human, okay? But I'd have to push in the same direction it's going. The velocity's to the right because it's going to the right. It's speeding up, so the acceleration's to the right. And I would have to push to the right. Now, moving to the right and slowing down, I think you know where this is going. If it's moving to the right and I want to slow it down, I have to push opposite the motion to slow it down. So the velocity again is to the right, the acceleration is to the left, and I have to push to the left. Now, folks, I think we'll all agree those were really trivial exercises. And this little chart is pretty basic. Every year when I do this lecture, I'm afraid that some engineer is going to walk past the door and start laughing. Oh, this is what they do in physics these days, okay? Because it's so trivial. However, the people that do not learn the lesson of this chart, again, will fail the next midterm. There are two vectors that represent the motion of any object, the velocity and the acceleration. The forces that we're going to be studying cause one of those vectors, but it's not the one that you want it to be. When you look at that chart, which of those vectors, velocity or acceleration, is caused by the force? Yeah, it's the acceleration. It's the acceleration. And that's a problem because it's a velocity vector that we can see out the front windshield of our car. That's the one that's so easy to visualize. Remember, we had a hard time with the acceleration. We had to do some reasoning. Is it speeding up? Is it slowing down? Is it turning? We had a hard time finding the direction of those acceleration vectors. But that's the vector that's intimately connected to the forces because the force causes the acceleration, not the velocity, the acceleration. Now look, the force is sometimes in the same direction as the velocity, but that's just coincidence. There's no physics there. But it's always in the same direction as the acceleration. See if your neighbor made the connection. See if your neighbor's on the bus. Okay. Let's go full circle now. Suppose I had the front two rows come up with pencils and all they can do is poke with their pencils. And I want this block to go in a perfect circle at constant speed. Based on that second tutorial, how should they poke with their pencils? What direction should they poke when it gets to them? Yeah, towards the center, or more accurately, perpendicular to the velocity, because we found that that would make it go in a circle at constant speed. If I wanted it to go in a circle and speed up, we would poke at an angle less than 90 with respect to the velocity. And if we wanted to go in a circle and slow down, we would poke with an angle greater than 90 relative to the velocity. You see how it all fits together? It all fits together. Okay, now I probably, okay. I spent your tuition on that, $14, we'll be okay, the rich school. There we go. Okay, so Newton's second law, net force causes acceleration, not the velocity. And when I'm saying net force, I'm saying total force. And the total force, or the net force, is the vector sum of all the individual forces that act on an object. Now, let me give you an example. Suppose I were to put this table up at an angle and put the dry ice on it so that it speeds up on its little layer of gas as it goes down the ramp, okay? Well, if I were to draw a three-body diagram for that block of dry ice, the first force I would put on it would be the weight force. And notice that I've labeled it by the earth on the block. I then asked, are there any magnets in this problem? No, be patient, Greg, they're coming. Okay. So I asked, what touches the block? Well, the ramp, only the ramp. Well, does it push or does it pull? Well, it's not a string, not a thread, not a rope, not a chain. It must push. Whenever one thing pushes on another, there will always be a normal force, by which we mean perpendicular force. Perpendicular to what? Well, perpendicular to this surface between the pusher, the ramp, and the pushee, the block. Okay, so a perpendicular force would be in this direction. Now, which of those forces is causing that block to speed up down the ramp? Both. Both. Trick question. Okay. Yes.
Why would that not be a pair, like a pair of force?
Oh, because of that layer of gas due to the dry ice subliming, it's floating on that layer of gas. So I don't hear any scraping going on. So there's no friction going on. There's just the normal thing. Okay. Now, when I say both of those forces cause the acceleration, I have to add them up as vectors. I'll get right to you, sir. And this is how we add vectors. There's the plus sign right there. I add them head to tail, head to tail. And then the net force, the total force, goes from the first starting place to the last ending place. And that's what causes the acceleration. And the acceleration is always in the same direction as the net force that causes it. Now, that's going to give me an acceleration, which is down the ramp, which is what we learned in the first tutorial. Now, there's a question in the back here. Old man running. Okay. What was your question?
So is a constant force a constant acceleration?
A constant net force will give you a constant acceleration. Yes. And we're going to learn the relationship between net force and acceleration in just a moment. Now, I want you to notice that on this chart that you made, nowhere on that chart is a net force. We got gravitational force, magnetic force, friction, normal, and tension. Those are real forces, that real things that you can smell, taste, touch, exert on other real things. But the net force is not a real force. It's a mathematical idea. It's the vector sum of all the real forces. Okay? And once I put all of those together, I put it into my equation to cause the acceleration. Now, let's go back to this pretest here. Okay. Hopefully, what we talked about will now make it clear. As this goes down through the snow, we have two vectors that represent the motion. And the question is, what should these diagrams scream? Should they scream that vector or that vector? Is the upward force going to be bigger than 50 pounds, equal to 50 pounds, or less than 50 pounds? Let's vote again. Okay, now you can click. Hopefully we'll all get it right this time. We'll show that that Greg's teaching has actually been effective, that we've actually learned something today.
If the net force acceleration is upward, has to be greater.
This is my favorite part of 105. The dynamics is the most fun we're going to have this semester. Really, Greg? This is the most fun that we're going to have? That's bad. No, it's going to be fun. It's going to be. Okay, last call. Yeah, it don't get no better. Oh, good, better. A is the correct answer. A is the, if you chose B or C, slap yourself. Okay? Or have your neighbor do it. This is the problem. That velocity vector is oh so easy to visualize, and it's the one that we have to ignore. The free body diagram has to screen the acceleration vector, not the velocity vector. If my acceleration is up, I got to have more force up than I have down. This diagram has to scream that acceleration vector. Now, when I started teaching at Montana State University 33 years ago, I started giving this pretest of the crate in the snow to my students, okay, the pre-med students. I had a wonderful colleague, a great teacher, John Carlson, who was teaching the calculus students, the engineers and the physics majors. And I tried to get him to put this, to use this pretest in his class. And he said, oh no, Greg, my students aren't confused. My students don't have a problem with this. They're fine. Well, I kept badgering him for 3 years. And finally, he put it in one of his lectures. And he was convinced that his students had a problem when his very best student was in his office after class screaming at him. But it's still going down. And the answer is, you know what? It never matters how it's going. It matters how the acceleration vector is pointing. Okay. And that's what we need to focus on. Now, let's change the subject and talk about mass. Therese, would you bring the two people that are next to you up here? And what are your names? Zach and Caitlin. Zach, Caitlin, and Therese, come on up here. I have two sets of objects, one clear and one white. And what we're going to do is we're going to have Caitlin, Zach, and Therese hold out their hands. And I'm going to give them each a clear one and a white one. And I'm going to give them 20 seconds to figure out which of the two has the most mass. Okay, which one has the most mass? And the time begins now. Da, 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 da. You can do anything you want. Da, 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 da. Da, 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 da. No. Okay. What do you think? Was that they're equal? What do you think?
I'm gonna say clear.
The clear.
Oh, wow. I was gonna say white, but I'm waffling.
You're waffling. Okay.
Unequal.
Well, let's give them a hand, folks. Somebody got it right. I don't know the answer. I picked these two to be very, very close because I wasn't interested in the answer. I was interested in how they found the answer. And you notice that they started out just holding them. I'm going to put words in their mouth. They're trying to think which one is pushing down on my hand the hardest. Okay. But that's weight. That's the earth pulling down on them and the hand getting in the way. And then right at the end, Therese did something that looked like this. Okay. And that is what physicists think of when we think of mass. Now, when we were in the 3rd grade or in, junior high, we define mass as how much stuff there is, as if you could have some special glasses where you could count all the protons and the neutrons and add them up. Not helpful, okay? For a physicist, mass is how hard it is to shake something, how hard it is to speed something up or slow it down. And it's very different than weight. Very, very different concept than weight. Let me give you an example. If I had a very heavy anvil, those huge things that you make horseshoes with, okay? If I were strong enough, I could hold that in my hand and it would push down with a huge weight force onto my hands here. It'd be a normal force on the hand, but it'd be due to the weight. Now, if I tried to shake that anvil, it would be hard to shake. If I took the anvil to the moon, it would weigh 1/6 as much. the earth pulls 6 times harder than the moon does. And so I could hold it very easily on the moon. It wouldn't push down on my hand nearly as hard. The weight force would be smaller. But if I tried to shake it on the moon, it would be just as hard to shake as it is on the earth. And if I went into deep outer space and could somehow anchor myself to the space, I could hold out my hand and this anvil would float just above it. I would feel nothing on my palm. It would be weightless. But if I tried to shake it, it would be just as hard in deep outer space as it would be on Earth. That's the mass. It's the same wherever you go in the universe for a particular object. Now, my oldest son, Joshua, is a straight arrow Eagle Scout, and we never had any trouble with him at all until one day we got a call and they wanted my wife and I to come down to the principal's office. And I said, oh, Heidi in trouble again? Oh, no, it's Josh. We got to the principal's office and the science teacher was there and he was mad. He was really mad. He said, Joshua ruined my lecture yesterday, my lesson. I was trying to teach the students that weight and mass are the same thing. And he just erupted. He just shouted out, are not. And I looked at that teacher and I said, are not. And he said, they are too. I said, are not. He said, they are too. I'm the science teacher. I wrote the book. I tried so hard to get that teacher fired. My wife made me go back and apologize to the teacher, to the principal, to the whole school. It was humiliating. But I went home that night and I hugged Josh, the tightest I've ever hugged him. And I said, I love you. You stood up for truth. You stood up for truth. Okay. They're different. They are different. Now, we're going to demonstrate mass with a demo that I call the hammer of death. Luke, you want to come up here and help me out? What we're going to do, we're going to put this piece of wood on this book and Luke is going to hammer that. I looked for a nail, but I could only find a screw. Just hit it. Yeah, just hit it. Whack on it. Do you need to get up higher? Right up there. Yeah. Okay, good, good, good. Now, what's protecting me? Well, maybe the squishy in this book is protecting me. So let's get rid of that. I've got here a lead block. And let's, okay. Yeah, just whack it. Okay, well, so now what's protecting me? Well, maybe it's a squishy in the wood. So let's just get rid of that. Okay, go ahead, Luke. Okay, go ahead. Yeah, that's good. Yeah. Let's give him a hand, folks. I should have asked what you got on that exam before I let you do that. Huh? Okay. So now I'm going to do a demo that is much scarier to me than that one. I call this the picnic of death. You've all wanted to do this at some time in your life. So let's see. I ran down to Desert Industry before class and bought some of this. Okay. The knife goes on the left or the right, people?
Right.
Right.
Good. I just testing you. Okay. Emily Post would be proud. Let's try this. Okay. Oh.
That's me.
Okay. Not bad for a Mormon boy. Yeah. Okay. Mormon boy, a Mormon boy. Oh, boy. How do you work it out? Oh, that didn't work the way I was hoping it would. Okay. Talk to your neighbor while I try again.
Hey,
Okay, I'm gonna be right back. Okay, let's try it again. That cloth just wasn't the right one. Wasn't the one I knew in the pre-existent. Okay. This morning I tried it with one of my wife's best china. That was a mistake. Better, right? Oh, no, that's just pity. That's just pity. Okay. Anyway, if you go to YouTube, you'll find that sometimes it works. I'm gonna have to find the smoother cloth, I think. If I were to do this experiment again, but instead of using the broken china that only cost $1, I use, say, paper, and I use plastic utensils, and then I used these guys here. What's going to happen now when I do it? What's going to fly off and what's not going to fly off? Yeah, the things that had little mass are easy to speed up, and so they take off. And the things with more mass are harder to speed up, and so they stay behind. And that's the way it's supposed to work. But as you can see, that doesn't always work. I would appreciate it if you never told anyone about this. Okay, this will be our little secret. Now, I told you before that during the summers, I used to teach classes for high school and middle school teachers that came from around the country and the world, actually, in what was called the Summer Teaching Institute in Seattle. And they did some experiments, 2 experiments that I'd like to tell you about. The first one, they started with a mass and they pulled with a certain force that they measured, and then they also measured the acceleration. And then they took that same mass and they applied twice the force, exactly twice the force. And what they measured was that they got twice the acceleration. And so from those experiments that they did, they found that acceleration was proportional to the net force. The second experiment that they did, again, they pulled on a mass and they measured the acceleration. But this time, instead of doubling the force, they doubled the mass. And what they found was that the acceleration got smaller, and indeed it got smaller by a factor of 2. And from this, they learned that the acceleration is proportional to 1 over the mass. And when we put these 2 experiments together, we find that the acceleration is proportional to the net force divided by the mass. Now, anytime you have a proportionality, you can replace that with an equal sign if you also put in a constant of proportionality. Now, that constant of proportionality depends on the units that we use. We've already decided to use meters per second squared for acceleration. We use kilograms for mass. You've learned that in your chemistry class. So what do we use for force? Well, if we use the unit called the Newton, we can make that constant of proportionality 1. And then we write that equation this way: F net is equal to the mass times the acceleration. And I would like you to read that equation this way. A net force causes a mass to accelerate. And this is known as Newton's second law. And it is the most useful tool that you will have in your toolbox through 105 and through 106 and through any physics class that you go through. This is the equation that you pull out more often than any other to solve a problem on your homework or on the exams. Okay, Newton's second law. And so you see from this equation that a Newton is just, it's the force that would be required to take 1 kilogram and speed it up by 1 meter per second every second. It turns out that 1 Newton is about 1/5 of a pound, about 1/5 of a pound. Now, folks, unfortunately, we've run out of time. We'll continue this discussion on Thursday, and we'll talk about Newton's third law, the most beautiful of all the physical laws.
It was a crazy night.
Yeah.
Well, I did that.
Over the rubric, make sure we at least.
Yes, anytime after. The.
You guys,
The speaker's like. Too much to know. We can't, you know.
I'll sit up, I think, so.
We can-
This way. Put down on your, no, the lever thing.
Yeah, you're right.
I don't.
Like I said, maybe he's a nice guy, he really. Teaching in the homework, so why not, right?
Okay, we.
You just need every word ever.
I think he should run, do it.
But
Teaching in college, now, like.
it's great. It was a lot of fun.
What is individual anyway? Yeah.
Doing-
They want the group.
Yeah, just stop by tomorrow, in my office, we go over.
And you make sure that I'm. So they. That I don't have this.
You would go forward.
Just a little bit, maybe.
I was just.
Thinking about pouring concrete today.
Yeah, come by.
We did.
Well, that's right.
Oh,
They're
thank
really
you.
expensive.
Yeah, we'll just leave it right there. Thanks.
I was wondering if I'd be able to come like earlier.
Oh, sure, yeah.
Yeah.
Yeah, regardless of which class you click in, you'll get credit.
Okay, awesome.
I just wanted to say thank you so much.
Oh, did you take it?
No, I'm going to take it right now.
Okay.
I got this and oh my gosh, shoot, and
Okay.
just slacking off. I'm starting to just.
It'll work.
Appreciate
Yeah.
it.
Yeah.
Thank you.
I was just gonna ask with tension, the force acting on the box, so let's say it's a string, I'm pulling my hand this way. Would the directionality of that force be towards the direction it's pulling?
Yeah.
I just want to double
Yep.
check that. Okay, sweet, thank you.
Well, I went right before class and bought this at Deseret Industries for $1. And it didn't go well.
Well, I doubt it will be missed.
Yes, it will not be missed. And I bought this because I thought it was gonna be a better cloth, but it turned out to be worse because it bunched up and grabbed things. And so I clearly made a mistake in buying it. So I wasted $2 worth of tuition money.
Purple cloth still in here? I used the purple.
The purple one is back in the closet. I'll go get it.
Okay.
We normally use the purple one.
Yeah, I now understand why that is the truth. I,
You probably should take that one out.
some things you should just learn from people who know instead of making your own mistakes. Okay, there's.
Thank you. Did you want to keep the red food coloring?
Say what?
Did you want to keep the red food coloring?
Yeah, I will. I'll
Okay.
keep that in my office. Wherever it goes, it makes a mess.
Here you go.
Thank you.